Hi there, Algebra 2. We are reviewing for a quiz covering sections 7.3, 7.4, and 7.5. So you'll notice at the start of each new section on your review guide, we go through and say what you need to be able to do from that section. So read through those objectives and make sure that you can check each of those off before you call it a night and call your studying done. So problem number 1 goes with our first objective from 7.3, where we need to simplify the following expressions involving e. In part A, we've got e to the negative second, e to the fourth, and e to the negative x. Well, our exponent properties tell us that when we are multiplying the same base, we need to add our exponents. Well, first we're going to add negative 2 plus 4. Negative 2 plus 4 is positive 2. And then we want to add that negative x, but we can't simplify it any further. So we call it e to the 2 minus x. Then we just combine our 5 times our 2, which is 10. So our final answer is 10 times e to the 2 minus x. In part B, we split up those radicals. So we've got the fourth root of 16. Well, the fourth root of 16 is just 2. And then the fourth root of e to the 24x, I would change that to a fractional exponent and call that e to the 24x divided by 4 so that we can see that we're going to divide that 24 divided by 4 and see that we have e to the 6x. So 2e to the 6x would be our final answer. And then in number 2, we are graphing our exponential functions involving e. Now remember, when we graph functions involving e, we can't do it using transformations quite as easily. We would still transform our x's if either of them had horizontal translations. Neither of them do, though. They have that r value in front of our x's, which differentiates our exponential growth functions involving e from our exponential decay functions. Because remember, if that r value is negative, that's going to be decay. Other than that, we really just graph functions involving e by plotting points. So we still want to plug in our typical 3 exponential x coordinates, -1, 0, and 1, and we just plug them straight into our calculator. So when we plug in -1, we have 2e to the, well, 2 times -1 would be -2, plus 1. Remember that your e button is the second ln key, which is near the 7, and we now know that that ln key is our natural log, which makes sense. So when we plug that in, our decimal approximation is about 1.27. And then we have 2e to the 0th plus 1. We get 3. And we have 2e to the positive second plus 1. And we end up getting 15.78. So because of that large y-coordinate, we are going to go ahead and count by 2's on our y-axis. Our x-axis, we've got plenty of room, though, so we're going to space them out. And those tick marks each only stand for 1. So our functions, when they are exponential, remember those have horizontal asymptotes. They're always y equals your k value. So our entire graph has shifted up 1, including our horizontal asymptote. So there is our horizontal asymptote at y equals 1, and then we plot our points. So we've got 1, 15.78, so that's like there-ish, right? Yeah. And then we've got 0, 3, and -1, 1.27. And sure enough, our graph does look like, whoops, well, if we could go through the points, that'd help. But it does look like exponential growth, just like we expected. Our domain for exponential functions will always be all real numbers, and our range is affected by that horizontal asymptote. So for us, it's going to be y is greater than k, or y is greater than 1. In example B, same process. We are plugging in coordinates for our x, -1, 0, and 1. And again, we just go straight to our calculator and plug those values in. When you do, you end up getting -0.35, plugging in -1. You get -1, plugging in 0, and you get -1.39 when you plug in +1. Our function is going to have a horizontal asymptote at our k value, y equals k, whoops, so for us, y equals -2. And so we can really kind of space out all of our tick marks this time. So every other tick mark is going to stand for 1 then. And we draw our horizontal asymptote down 2 this time. And we plot our points. So we've got one about right here, and right here-ish. And sure enough, this looks like exponential decay because of that negative r value. And our domain for this exponential decay function would be all reals, just like any exponential function. And our range is affected by our k, so for us, y is greater than -2. And then lastly, on the first page, we've got problem number 3 involving Citibank. So Citi offers a savings account that provides continuously compounded interest for its customers. So right away, because we see that word continuous, and especially continuously compounded, we know we're dealing with A equals PE to the RT. Then from here, we just have to piece together what goes where. So for its customers, the annual rate of interest, that would be our R, or it helps us find R. It's going to be 0.02, because remember 2% needs to be as a decimal. And we've got our good friend Sheila. She's investing an initial principal amount of $1,500. So there's a value for P. And how much will she have in 6 years? That is a value for T. We plug it all in. So A equals 1,500 times e to the 0.02 times 6. And we make our calculator do the majority of this work. We end up finding that she now has $1,691.25. Notice that this is a different function that we use, a different formula than our regular compounded interest, or interest compounded n times per year, because of the word continuous. So our continuously compounded functions tell us to use A equals PE to the RT.